we're good.
Right.
We're very happy today to have Professor Brooks Thomas from Lafayette College. Professor Brooks Thomas did his PhD at the University of Michigan, and then he held postdocs at the University of Arizona, the University of Hawaii, where he was one of my postdoc mentors, and then at Carleton. Now he's a professor. He works on dark matter, cosmology, phenomenology. He's here today for the full day and then tomorrow as well. So if you'd like to schedule a meeting or just pull him aside for a chat, definitely could be arranged. And there could be maybe 1 or 2 spots left for dinner if you want to come to dinner. So let me know if that's the case. So without further ado, Professor Brooks Thomas will tell us about stasis.
Great, thanks, Joe. I'm Brooks. Great to be here. This is my first time in Kingston. And I'm going to talk a little bit today about a phenomenon called cosmological stasis or cosmic stasis, which my research collaborators and I uncovered a couple of years ago and whose consequences we've been exploring ever since because we think it's kind of an exciting, interesting, novel possibility that seems to arise reasonably generically in certain kinds of extensions of the standard model and can give rise to all sorts of interesting observational effects that we might be able to actually probe. So this is based on a whole series of papers here, including this first one here that basically kind of proposed the phenomenon, as well as a number of others that have proposed different realizations of it and explored different kinds of consequences of it. So I'll hopefully over the course of the talk kind of give you a sense of what stasis is, why we think it arises reasonably generically in certain BSM contexts, and what stasis can do in terms of observation. Okay, why is that not? Okay. That's frozen. That's interesting. There we go.
First example of stasis.
All right, I cannot navigate this if I don't have if I'm not hiding the meeting controls.
Oh, okay.
So.
I think it'll be fine.
All right. Well, we'll give it a try.
Sorry.
Yeah. All right. So with hopefully no more further ado. Oh, that's not going to be great, is it? Ah, man.
Controls and then clicking on the presentation.
Okay. There we go. Okay, perfect. All right. So let's begin then with the following observation. So there are a lot of theories beyond the standard model that give rise to towers of massive unstable states with a broad spectrum of masses, cosmological abundances, and lifetimes. And that's sort of the point where I'm going to be starting motivationally. So such towers are a generic feature of, for example, string theory, theories with extra space-time dimensions in addition to string theory, scenarios with confining hidden sector or dark sector gauge groups, which give rise to towers of bound state resonances, and scenarios which give rise to primordial black holes with an extended mass spectrum, where the black holes themselves constitute the tower of states. So in many of these scenarios, such states can give rise to astrophysical signals, signals at colliders, all sorts of things that you can see and detect in typical ways. In other scenarios, however, they are too heavy or short-lived to have physical effects that we can detect. However, this doesn't mean that there are no consequences that we can probe from these kinds of theories, because of course we have early universe cosmology. the presence of such towers, as we'll see, can have a significant impact on the way the universe evolves. And in particular, we're going to be focusing on the part of the cosmological timeline here before the nucleosynthesis epoch and neutrino decoupling. So after this, modulo, of course, a lot of anomalies like the Hubble tension and sigma 8 tension and a lot of things that are coming out of DESI and experiments like that. We at least know reasonably well what's going on here, and things here are far more unconstrained. So we're going to be focusing primarily on what happened between the end of inflation and the beginning of nucleosynthesis. What I'm going to argue here is that towers of this sort can give rise to epochs of what we call cosmological stasis. These are epochs in which the abundances, in other words, the fractions of the total energy density made up by different kinds of stuff, different cosmological components like matter, radiation, vacuum energy, that these abundances can actually remain constant, meaning different things like matter, radiation, vacuum energy are sharing the energy density of the universe with constant abundances for a very long time in logarithmic time, very long number of e-folds. So these epochs, as we'll see, arise frequently in theories with towers of states like this. And when they do arise, they are also global dynamical attractors in those cosmological systems, meaning that if your theory admits a stasis solution, the universe will be driven toward that state. Okay, so what is going on here? All right, so to see what cosmological stasis is, it's probably easiest to start out with a simple example. So let's start by considering a universe which consists of two different kinds of stuff, matter and radiation. Matter, by matter, we mean non-relativistic massive particles. So these are things where as the universe expands, their energy is mass energy, so the energy density is going to scale like the volume to the -1 power, or the scale factor, through which distance scales to the -3. Radiation is going to scale, because there's an additional redshifting factor, to the -4. So the equation of state parameter cosmologically for matter is W equals 0, for radiation is -1/3. And so if we write down the dynamical equations, the Boltzmann equations, that govern the evolution of these energy densities, matter is going to go like this, radiation is going to fall faster, and of course, in the long term, that means matter is going to win out over radiation. If two things have different equation of state parameters, their energy densities are going to scale differently with the scale factor, and one of them in the long term is going to dominate. That's the standard law. Of course, what we are assuming here by writing these Boltzmann equations this way is that there are no other processes involved other than cosmological expansion. So, okay, first, to see how more interesting things might happen, let's rewrite these Boltzmann equations in terms of the abundances, so fractions of the critical density of the universe. So the matter abundance, or the fraction of everything that's in matter, goes up and eventually just plateaus at 1. The radiation abundance goes down and becomes negligible, and the Boltzmann equations look like this. So expansion drives matter abundance upward, radiation abundance downward. Now, here is how things change in the presence, potentially, of additional terms. So let's imagine that beyond expansion, there is also some sort of pump, if you will, or a set of source and sink terms that serves to transfer energy density from matter to radiation. So minus P for pump here, plus P for pump here. And notice plus minus, minus plus. So interestingly, if we take a look at these equations, there exists the possibility that these two terms on the right side, if they both had the correct time dependence, could cancel each other. Could cancel each other for a very long time. And in fact, we can tell exactly what this pump term should be doing in order to cancel the expansion of the universe contribution by just the fact that if these two cancel each other out, that means that the matter abundance and the radiation abundance should not change, and therefore these two should be constants. The only thing in this term, therefore, that has time dependence is h, which is the Hubble parameter, tells us about the expansion rate of the universe, and that generally goes like 1 over t. So, in a universe like this, it certainly will go like 1 over t. So, what this means is that this pump term has to go like 1 over t. And if it does go like 1 over t, there's a possibility that these two could cancel. Okay, so how can such a pump term arise in practice, and how could we get a 1 over t behavior out of this? Well, one natural mechanism is particle decay, right? If I have a bunch of heavy, massive particles sitting around in the early universe, non-relativistic, they can decay into much lighter particles. Those act as radiation, predominantly kinetic energy, and that's a way of transferring energy density from matter to radiation. So particle decay is one possibility. Of course, we know how the time dependence of the decay of a single species of particle works. This is exponential decay, right? That is not 1 over t behavior. So the exponential decay of a single matter species over a relatively short period is not going to be sufficient for achieving stasis. However, as we'll see, this is where the tower comes in. If we have a tower of matter states, let's call them phi sub L, where L goes from 0 to n, some large number n minus 1, where L labels these particles in order of increasing mass. And let's say that these particles have some spectrum of decay widths, gamma, and some spectrum of abundances, omega sub L naught, at some initial time t naught. It is, as we'll see, possible for such a tower to give rise to a 1 over t behavior and satisfy these pump conditions. Moreover, as we'll see, it will also tend to. This ends up being an attractor state. Okay, so to provide, again, a little motivation of why this should be interesting to us and isn't just, some weird fine-tuned example, let's consider what a tower of matter states with, again, W equals 0 for matter. Let's consider a tower of matter states that have these following scaling relations. And I'm going to motivate these scaling relations from beyond the standard model theories. So the masses, let's assume that the masses scale like some zero mode mass m naught plus some parameter with dimensions of mass delta m times the index that labels the mode L to some exponent delta. So basically, power law with respect to this index. Let's assume that the decay widths and abundances both scale like power laws of the mass. So gamma sub L equals gamma naught, the decay width of the lightest mode, times ml over m naught to some scaling exponent gamma. And for the initial abundances, same thing, but with scaling exponent alpha. Okay, now I've just proposed this, but the motivation for this actually falls out of a lot of BSM scenarios. So how would we get a value of delta, or how would we get a mass spectrum that looks like this? Well, kk excitations of a 5-dimensional scalar field, indeed in different regimes depending on the radius of the extra dimension and certain other mass parameters that arise, give you naturally delta equals 1 or delta equals 2. If we're talking about the bound states of a strongly coupled gauge theory, you get a scaling relation like this with delta equals 1/2. So basically, these are mass spectra like this are common things within the framework of BSM scenarios. So what about decay widths and abundances? Well, for decay widths, if you imagine that these particles are decaying through some non-renormalizable higher dimension operator, this operator, if it's of dimension d, will naturally have gamma here be 2d minus 7. So that's a very natural thing. And alpha, well, what are the initial abundances? That depends on how these states are produced in the early universe. So there are all sorts of different mechanisms, which I won't get into, everything from misalignment production to thermal freeze-out to gravitational production. We can talk more about these individual cases offline. The point is not what each individual one gets, but the point is that all of these different commonly studied production mechanisms give you scaling relations like this with particular values of alpha, roughly. So the point is, these are not crazy things to assume. These are things that fall out of theories beyond the standard model quite readily. Okay, so given that, and the next few slides are kind of technical, so I'm just going to elide over most of them. But basically, so if we want stasis, the idea, of course, again, is to assume that the abundances, as we said before, are constant. So because the Boltzmann equations for the individual fields look like this, so these are just like the Boltzmann equations I wrote down, only I'm writing explicitly here the energy density transfer term from each one of the states, rho sub L, into radiation. And so for radiation, we have a sum of all of those. If I sum up the total matter abundance, in other words, take this, convert this into an abundance by dividing by the critical density, and then basically sum up all of the contributions for all of the different fields. This is what we get, written in terms of abundances. So our stasis condition then, saying that this is 0, is equivalent to saying that this is 0, or in other words, saying this. So if the left and right sides of so basically if the left and right sides of this equation are equal, that's when we get cosmological stasis. Okay, so how are we actually going to get this from a theory involving multiple different scalars or multiple different states? So the Friedmann acceleration equation tells us what the Hubble parameter is doing. So the Hubble parameter evolves like this. And you can distill that into an equation for the Hubble parameter here. And so basically, here's our substituting our result for the Hubble parameter into here, basically gives us this equation here, as long as during stasis, assuming that this is satisfied during stasis, so this is our stasis condition. And just using the fact that summing up all of the different matter states gives us the overall matter abundance. So that's what this omega m bar is. So during stasis, this matter abundance would be omega m bar, and this is the condition we need to satisfy. So we can also rewrite this by combining these two conditions and write it as a ratio like this. So if this equation or this equation is satisfied, we're going to get stasis. I will not bore you with the details. You can write the individual abundances in terms of an exponential decay factor, a redshift factor, and the initial abundance. All of these have different scaling relations, and you do, basically integrate sum over the entire tower in the limit where delta m is small. You can turn this into an integral and essentially basically show that this overall contribution on the left side of this equation here, the sum over here looks like this, where we have defined eta equals alpha plus 1 over delta. And then we can see what the denominator of that equation is, substitute things in, and basically what we get is a situation that looks like this. Thus, we have our pump condition satisfied. So once we're substituting everything in on both sides of this equation, we basically reduce to something that looks like this. We have a 1 over t dependence and a 1 over t dependence after we plug both of these things in on both sides of this equation. What this means is that to be in stasis, we just need eta over gamma. So eta is determined by the fundamental scaling relations here, alpha plus 1 over delta, and gamma is another parameter that tells us about our fundamental scaling relations. These fundamental scaling relations are going to tell us what the abundances of matter and radiation are during stasis. So alpha, gamma, and delta are going to tell us what omega bar is. The balance of matter and radiation during stasis are going to be determined by those underlying parameters. And we can then just solve this equation, and here are what the matter and radiation abundances look like. Okay, that's a lot of technical stuff. Let's skip to the real end goal here, which is to see cosmologically what this looks like. So this is a real numerical simulation involving 300 fields of exactly how things evolve in a cosmology like this. And we are going to start, we're not going to start the universe in stasis. We're going to start things far away from stasis, as far away from stasis as we can, by assuming, for example, that all of the energy density of the universe is initially just in the decaying matter states. So imagine that a time way before their lifetime where they haven't really, the lifetimes of the most unstable ones, so that none of them have decayed yet. Then, eventually, once we reach the time scale associated with the lifetime of the most unstable, heaviest one of these, they'll start to decay. And as they start to decay, the total matter abundance, shown here in orange, will begin to drop, of course. But there's feedback from the Hubble parameter because this changes how the universe evolves. The balance of matter and radiation changes. And that feedback causes the universe to settle in for a very long number of E-folds. So this is basically the log of the scale factor here. So a long number of E-folds where omega matter is approximately constant. And of course, omega radiation in this two-component universe is also approximately constant. Now, again, I have chosen particular values of alpha, gamma, and delta, so when I plug them into the stasis abundance relations I showed you on the previous slide, I get a 50-50 split. But again, as we saw before, that's contingent on what the values of alpha, gamma, and delta are. So if I change the scaling relations, I don't wreck stasis, I just get a stasis with a different balance of matter and radiation. Not 50-50, but maybe 70-30, maybe 80-20. Something like that. We can also see, by the way, how the interplay between what the individual modes are doing here gives rise to stasis. Each of the matter modes is its abundance is sort of rising. And why is it rising? Well, it's rising because our universe is an admixture of matter and radiation, and because these are matter, their abundance rises in a universe that is not matter-dominated, but is an admixture. And it rises up until a point where we get to a time scale right around where its lifetime is, and then it begins to fall exponentially. And so, as each field goes down, another one comes up to take its place. And as each one goes down, another one comes up to take its place. And the tower collectively conspires to give rise to this behavior, where things are constant. Now, this is pretty cool, but what's even cooler, two things. First of all, backing up to get a sense of what this implies, because our universe is an admixture of matter and radiation, the effective equation of state for the universe as a whole, which determines how fast the universe expands during this period here, this stasis era, is a weighted average by the individual equation of state parameters for matter and radiation of the abundances. So what we get here in this example, where we have a 50-50 split, well, for matter, the W is 0. For radiation, W equals 1/3. What we get is a 1/6. Now, so the universe is kind of mocking up a perfect fluid with an equation of state parameter of W equals 1/6. That's weird. That's not something that typically happens in normal cosmological models. And yet, in these models that are motivated by BSM theories that give rise to towers, sure enough, this can happen. Now, you might wonder whether or not this is all just finely tuned and dependent on initial conditions, but it's not. The reason is, and this is really what deeply makes stasis interesting in my opinion, is the universe is propelled toward it. It's a global dynamical attractor. So, in a scenario where, and I have to say the variables that we're plotting here, this in terms of require a little bit of explanation. So here's the matter abundance. And normally you would think I might plot the Hubble parameter on this axis. It turns out that as a proxy for the Hubble parameter, it's easier to plot the average matter abundance since time equals 0. Believe it or not, that's just, through a few changes of variables, a proxy for Hubble. So these two variables, in that space of two variables, let's see where we evolve to. Here is the stasis state, again from the previous example. So we have a 50-50 split, so matter abundance is 50. And of course, in the long term, the average should drift toward 50 at 50-50 as well. No matter where we start on this diagram, the universe eventually evolves toward this stasis state. We are driven there. Moreover, regardless of what the relationship is between the decay width of the heaviest state and the initial value of the Hubble parameter, if the heaviest state, if this ratio is very, very, very large, initially we're going to have a lot of energy density just dumped into radiation right at the get-go, because we have a very large decay rate, decaying very fast. But then it will sort of creep on back toward the stasis state. And if this is smaller, it will evolve downward toward the stasis state. So stasis is a very robust attractor. In other words, if your system admits stasis, if you have scaling relations that have alphas, gammas, deltas like that, you are going to drift towards stasis. Stasis is going to be an inevitable part of that cosmology.
You probably mentioned this, but so n is logarithmic time or logarithmic scale factor?
Logarithmic scale factor, yeah. Number of e-folds, so it's basically log e over some reference, log a over some reference a, yeah.
Okay. And things like the horizon, I mean, this is sort of a kind of radiation dominated, so you're not doing what inflation could do or something like that.
Okay, I will talk later about actually you could do, it turns out, what inflation could do. Not in this kind of scenario, but there are other versions of stasis that involve vacuum energy that can give you accelerated expansion. Great. Okay, so what this basically means, kind of, comparing to the traditional picture here of what the cosmic timeline looks like. So traditionally, the idea in the standard cosmology is that, so basically you have some, inflationary epoch, thank you for the segue, early on, and then the universe, after maybe the inflaton begins oscillating in the bottom of its potential, and you get some sort of brief matter-dominated period. Then you have reheating, things become radiation-dominated for a very long time, and then you segue into the, dark matter and baryons matter-dominated epoch at the end, which is, of course, segueing into another dark energy-dominated epoch now. So that's the traditional picture. Here, kind of shown, here I'm showing sort of this in terms of abundances versus log A. And what we're seeing here is basically the universe essentially consists, this timeline consists of a set of single component epochs, one after the other. What we see in stasis is something where we have a balance, kind of this yuan-yang hot pot, which one of my collaborators thought was a great analogy, and I agree. So where the idea is that you have something that is the hot side and the cold side for different people who like different spice levels. In the stasis picture, you basically have, for example, you could have, after reheating, maybe one of the matter fields collectively could end up dominating the energy density of the universe and then decaying, and that could give rise to a cosmological stasis. Again, here's the 50-50 example. It doesn't have to be a 50-50 balance. But for a significant number of e-folds, the universe could be in stasis. So this is a new kind of cosmological epoch, and one whose consequences it would be interesting to explore. So there are, again, a lot of other realizations of stasis that I don't really have time to get into in this talk. So stasis can also, as I was saying, involve vacuum energy. A natural realization of such a stasis would be if I have a tower of oscillating scalar fields with a spectrum of different masses, which transition from overdamped to underdamped behavior. So in other words, I was about to say if I had chalk here, which I apologize to the people on Zoom, but if you had, a set of fields where you had, so for example, some fields had a fairly broad potential and other fields had a fairly narrow potential. So this is as a function of phi. Here's v of phi, assuming that these are basically, the potentials are basically decoupled. Fields like this, which are basically higher mass fields, are going to end up starting to oscillate earlier on than the lower mass fields. And therefore, you can get sort of different fields turning on or going from overdamped to underdamped at different times sequentially. And this can also give rise to a stasis epoch. So that's another possibility. You can even have a stasis that involves more than two components. You could have a stasis involving vacuum energy, matter, and radiation, and that's something I'm illustrating here. Won't go into the details, but that is possible. In certain scenarios, stasis can even arise due to annihilation rather than decay, so there can be other mechanisms for transferring energy density. There are all sorts of different possibilities. So we, again, believe that stasis is a very robust phenomenon. There are a lot of different incarnations of it, and that it can arise in a lot of different contexts. Okay, so in the, I guess, 20 minutes I have remaining, I'll kind of focus a little bit on some of the observational consequences of stasis. Because not only is stasis something that is motivated from the top down, it's also interesting from a bottom-up observational perspective. So in this talk, there are a couple of things that my collaborators and I have been pursuing recently. One is that stasis can modify predictions for CMB observables, such as the tensor to scalar ratio and such. I'm not really going to talk about this unless anybody really wants me to. So talk to me offline if you're interested in this. I'm going to focus on what I think are the two biggest kind of smoking guns, which are modifications of the stochastic gravitational wave background. There are also all sorts of gravitational wave signals that can arise in scenarios like this, and the way that stasis modifies the way that density perturbations evolve in the early universe. So again, I'm going to kind of cook the books a little bit in the sense that I'm going to show you in the most interesting context possible what these can do. But I do want to emphasize that these effects are actually fairly generic, and they arise in basically any kind of stasis sort of scenario. They're sort of generic consequences of the phenomenon. But as we'll see, there's certain realizations of stasis that can give rise to some really surprising, really interesting signals here. Okay, so first of all, gravitational waves. So obviously, these are interesting. And the context that I'm going to talk about gravitational waves in is a stasis scenario where the spectrum of states that gives rise to stasis are primordial black holes. So there are a lot of ways in which primordial black holes can be generated in the early universe. One is the collapse of perturbations with a scale invariant power spectrum after inflation. A lot of people have studied this, and basically you end up getting a sort of black hole mass spectrum that kind of looks like this. So it is governed by, so basically MI is the initial mass of the primordial black hole. Alpha is a scaling exponent, which is, apologies for the notation, different in meaning from the alpha before, different papers, different coefficients. But basically the idea is that, lower alpha, it's a little bit more, tilted towards heavier masses. Higher alpha, it's a little bit tilted more towards lighter masses. And this is, of course, within a particular mass range in which the perturbations early in the universe are enhanced between some minimum and maximum mass values. So to give you an idea what the constraints are on the parameters of this scenario, alpha, and this mass range, the m min and m max. So alpha, basically, so the value of alpha actually turns out to be determined by the equation of state parameter for the universe during the epoch where the black holes collapse. So there's a one-to-one correspondence between that equation of state parameter, we'll call it W sub c for collapse, and alpha. And if we want this to be after inflation, that means the universe should not be inflationary during this epoch, so WC should be greater than -1/3. We also want the primordial black holes to eventually maybe to not just sort of be suppressed into oblivion, but eventually come to dominate the energy density of the universe, which will mean that we actually will want this to be even higher, to be bigger than 0. So this condition tells us that alpha better be between -2 and 0. We're actually going to make the stronger condition that WC is going to be greater than 0. So this is going to be between -2 and -1. Those are the values. So as far as the m min and m max are concerned, there's an upper, so there's a Planck upper bound on the Hubble parameter associated with the pivot scale that places a lower limit on what m min can be. We want to make sure that the black holes that are very light tend to evaporate, and if they're evaporating during while Big Bang nucleosynthesis is happening, that can disturb things, so that puts an upper limit on the masses of these black holes. So this kind of gives you an idea of roughly what the scales are. Okay, so just to kind of provide sort of a broad brush synopsis of what's going on. So primordial black holes, the energy transfer mechanism here is Hawking radiation. Black holes have a temperature, it looks like this, and that means they radiate energy off into radiation. The rate of change of the mass of a single black hole from this looks like this. This epsilon is a gray body factor, and within the regime we're interested in, it's approximately constant. That means that the primordial black hole evaporates completely at a lifetime that goes like its mass cubed over some factors. And so if we want to know how the energy density of the black holes in general behaves as a function of time, we need to integrate over all of the contributions from all of the masses, the primordial black holes which have different masses and which are evaporating and sending energy density from matter to radiation. Okay, so we've got our pump. Does this give rise to stasis? Well, indeed it does. Here are some results from this model, and this is for this parameter alpha being -5/2, -3/2, etc. We see that if the universe starts in a primordial black hole dominated epoch, that it will evolve into a period where the abundance of primordial black holes remains flat for a very long time. The rest is, of course, the radiation that they evaporate into. So again, this is a cosmological stasis. In this system, it is also, this probably should look uncannily familiar, kind of like the last one. In this scenario as well, it is also a global dynamical attractor. Okay, great. So there's a lot of interesting phenomenology that can arise from this. So basically, the history of the universe in this scenario, so after inflation, there's this epoch where the PBHs are generated. Then there's another epoch where the PBHs dominate the energy density of the universe. Then, of course, there's the stasis, which can last a long time. And then we get the regular old radiation and matter domination epochs after stasis ends. We segue into back to the standard cosmology. So, and of course, primordial black holes, I should say, if you're worried about, accretion and mergers and things like that, we've studied this. A paper's coming out imminently. Primordial black holes can merge. They can also accrete. These don't really disturb anything significantly for primordial black holes in this mass range, it turns out. So we did a study. Those are the results. Okay. So how does this actually impact observation? Well, it can impact the gravitational wave background. Why? Well, okay, the differential gravitational wave energy density per logarithmic co-moving wave number, generally we can parameterize it like this. The differential amplitude, that's this h sub k, depends on when the perturbation mode re-enters the horizon. So that's going to look like this. When things enter the horizon is going to depend on what your cosmological timeline looks like and how Hubble evolves. So going forward, so basically, the wave number k, which enters the horizon at scale factor a, scales with ak according to this relation here. So this implies that our differential spectrum here looks like this, where this exponent of k, this xi, depends on w, the equation of state parameter during the epoch in question. So in the standard cosmology, if you do a little arithmetic, you will see that if we put in w equals a third, that's radiation, this thing vanishes, and you get basically a completely flat spectrum. Okay, what do you get in stasis? Well, you have a lot of different epochs with a lot of different equation of state parameters, and things look way more complicated. You're going to get distortions wherein different regions of the gravitational wave spectrum are going to have different slopes and different kinks. The interesting thing, so here's an example. I'll ask you to focus kind of on this plot here. So what I'm showing is a function of gravitational wave frequency here, what the gravitational wave spectrum, the abundance, differential abundance of gravitational waves per unit log f looks like for m min equals 100 grams, m max equals 10 to the 5 grams, and a number of different values of alpha, which are these different curves. So there's a lot of behavior here, so I've kind of scaffolded it. I'll show in a minute. First thing I want to help us with to get us all our bearings is that so all of these gray blobs here, these correspond to detector sensitivities of different experiments. Now, again, I have cooked the books a little bit in the sense that this normalization is not something that is necessarily fixed. I am showing you something plausible that doesn't have to be that case, the case, but just giving you a sense that one could in the near future have some interesting signals within interesting regions of the gravitational wave spectrum. So what do all of these different kinks and things correspond to? Well, basically, again, different slopes correspond to modes that are entering the horizon during different epochs. Things that are over here, where everything is flat, are entering the horizon after the universe has already become radiation dominated and we've segued back to the standard cosmology. Going backwards, these lines here correspond to modes that entered during stasis. This slope is determined by alpha, which is determining the equation of state parameter during stasis. Then these little kinks here are the ones that enter during the primordial black hole dominated epoch right before stasis. And then as we go either up or flat or down some more, depending on what the value of alpha is, these are the ones that enter during the primordial black hole formation epoch, where the equation of state parameter is WC. So the important thing to realize, though, remember, WC told us what alpha was. There's a one-to-one correspondence there, as we saw before, which means that because alpha is telling us what W is during the stasis epoch, there's a correlation between this slope and this slope. If you can get access to both of these slopes, that's pretty compelling evidence for stasis. There's a lot of other phenomenology here. Feel free to ask me about these sort of corn dog looking things later on. I have lots to tell you about that. But basically, that's the overall idea.
Sorry, very quickly, this
Yeah.
doesn't include any of the gravitational waves produced directly by the black hole evaporation.
No, it does. So that there will be an additional contribution from those. We have not analyzed that yet. There also can be additional contributions, for example, when you have the potential, for example, when it varies differently during a stasis epoch, the variations in the potential can source gravitational waves as well. There are other contributions in addition to these that could also be interesting in different frequency ranges. Yeah, so this is just the tip of the iceberg. Yeah. Okay, so
these gravitational waves were produced during inflation.
yes, these are gravitational waves that are produced during inflation, and it's just that when they enter the horizon is modified by the stasis. So this is all just, this is why I say this is generic.
But it must be degenerate with non-standard models of inflation.
Yes, that is true. That is indeed. So there is a little bit of a not one-to-one inverse problem. Absolutely, absolutely. And it may be that those sort of other kinds of gravitational wave contributions are going to be the key that allows us to break that degeneracy, one would hope. But I can only speculate at this point. Yeah, no, you're absolutely right. Okay, and number 2 in the 3 minutes I have, density perturbations. Okay, I'll try to go as fast as I can. So I've kind of said earlier that the universe kind of mimics a perfect fluid with a weird equation of state parameter that's given by this average equation of state parameter W bar during stasis. And well, that is certainly true at the level of the background cosmology, right? How the rate of cosmic expansion. The question is, to what extent is this equivalence broken at the perturbation level? And in order to kind of do an apples to apples comparison here, what we're going to look at is how a spectator component, let's call it chi, with the following properties, how do its density perturbations evolve? And what this chi is we're gonna assume this chi is gonna be, is it's basically, we're gonna take a look at a massive matter component, so W chi equals 0. We're gonna assume that during the stasis, it has a really, really small energy density, otherwise it would muck up the stasis, the balance between matter and radiation during stasis and give rise to problems with the dynamics. We don't want that. And it interacts with other components only through gravity. In other words, it acts like a population of decoupled frozen out dark matter particles. And indeed, that's the motivation. So we should think of this as sort of what is stasis doing to a frozen out dark matter abundance or dark matter perturbations. So let's take a look at how the density contrast delta rho over rho behaves during stasis for a component like this. So to get our bearings here, regardless of what's going on, this is a spectator. It has no source or sink terms, so the stress energy is conserved in that sense. We can distill out of that an equation of motion for delta, which looks like this. Here is a big old source term. This phi is the Bardeen potential. Up to a minus sign, it's the gravitational potential. So we can basically think of what we need to know is how the gravitational potential evolves. So the solution to this is just a second order differential equation with a source term, and we can apply the method of Green's functions to solve it. So here is, all we need to do is figure out what phi is doing, and then we know what's going on here. What is phi doing? Well, the Einstein equations tell us what phi does. So phi turns out to be governed by a second order differential equation with a source term. This falls out of the Einstein equations. And the structure of this term is actually the important thing. So let's look at this source term very carefully. First, we got a bunch of constants, but beyond that, this is basically a weighted sum of over all of the different individual cosmological components x, with different equation of state parameters or whatever, of their background energy density times their density contrast, so basically delta rho here, times the difference between the overall equation, average equation of state for the universe in general. So in stasis, this is W bar for a perfect fluid dominated universe. It's the W for the perfect fluid, minus the sound speed squared for that fluid. And that's what it is. So this term, as we're going to see, is the source of what's different between these two different fluids, or these different cases. Perfect fluid. Let's start with a perfect fluid. So with a perfect fluid, basically, there is only one cosmological component with a non-negligible energy density. So everything else but the perfect fluid falls out of this sum. Since the perfect fluid is dominating the equation of state for the universe, its W here is equal to the perfect fluid's equation of state. C squared for the perfect fluid, if this is a perfect fluid, by definition, if this is its equation of state, then Cs squared is also going to be equal to W for perfect fluid. This vanishes. This was shown by these folks. And you basically get solutions for phi that look like Bessel functions times some polynomials. They go down and they ring. And delta, when you plug it into the Green's functions, look like this. What happens is after a little bit of transient behavior, everything plateaus. Now, as a contrast, we should remember that in the standard cosmology, when I have radiation domination, how do the density contrast of dark matter behave? It grows but logarithmically. But this is even worse than logarithmic. This is not growth at all. So after this little pip up, it does nothing. So this is actually a suppression. And that's kind of what these folks showed. Okay, what happens during stasis? In stasis, there are multiple components with non-negligible omega x. In a matter radiation stasis, this W is W bar, and we have multiple terms in this sum. For matter, C squared is basically 0. For radiation, under certain cases, you can have this slightly be different from 1/3, but if this is just a pure radiation component, this is 1/3. So let's take a look at that simplified case. The important thing is that qualitatively there are two terms here, so this source term doesn't vanish. What this tells us is that phi sub k, instead of going down and ringing like a Bessel function, like the blue curve, the perfect fluid thing, what this does is it goes down monotonically and much more slowly. What does this mean? Here's the upshot. The upshot is that here are for the dashed lines corresponding to perfect fluid domination. For stasis, and these are curves for different modes with different wave numbers that are entering the horizon at different times, horizon entry being indicated by this vertical line here. When they come in after that little transient period, they're growing like a power law. Now, what is that power law? Here's the power law, here's the power law exponent, and it's totally not obvious from this big glob of symbols, but depending on what W bar is, this goes from, Q goes from 0 to 1. If the vast majority of the energy density during stasis is matter, it will be very much appropriately like a matter-dominated epoch. With a matter-dominated epoch, we know that delta, the standard law is things grow linearly. So this never quite grows linearly. It's between logarithmically and linearly. Actually, it turns out that the transient ends up dominating the long-term behavior when this goes to 0, and you basically end up getting a log out of the deal. So this interpolates between matter domination and radiation domination. So stasis, even in the way the perturbations are evolving, is interpolating between matter and radiation domination. Why do we care? Well, if we have an enhancement to the growth of the matter density, that's affecting the linear matter power spectrum here, which can affect cosmic structure. And in particular, these are, giving you an idea of sort of what the best case scenarios with these scales are. You can't affect things at arbitrarily low wave numbers because there are bounds on how late stasis can be. But you can affect things that are around the asteroid or solar or Earth, solar or Earth mass level in terms of what the size of the clump, the perturbation clump is. So basically, you can produce little tiny dark matter halos called microhalos. This is similar to the way things work in matter domination, but the spectrum of these things is likely very different in stasis, and these can give rise to all sorts of interesting like microlensing effects and stuff like that. Just to conclude, and sorry, I've gone a couple minutes over, so I'll just stop here. Stasis is a novel kind of cosmological epoch that arises in well-motivated extensions of the standard model, those that involve towers of unstable states. Stasis is a global dynamical attractor in these kinds of systems, so the universe tends to evolve toward it. And also there's a natural way that the universe evolves out of stasis. Once you run out of states, the lightest and most stable one decays, you have no more states anymore, you're radiation dominated. Okay, So there's a graceful exit from stasis. And stasis can also give rise to all sorts of interesting observational consequences, modifications of the stochastic gravitational wave background, and as Aaron and other folks mentioned, other kinds of gravitational signals as well. They can also give rise to a difference in the evolution of density perturbations for a matter component that can give rise to interesting small-scale structure effects. Okay, thank you, and thanks for begrudging my 5 minutes overtime.
I think the minutes were accounted for in the nice questions we had during the talk, so we have time for a few questions.
When you were deriving sort of the conditions for stasis, you said like the VSM mass states are separated by some delta m times the index to the power. And then you said that delta m gets really small. Is that strictly necessary to produce stasis?
Okay, good question. So there is a there's kind of a criteria sort of that you can sort of derive. Basically, what needs to happen is if there's a big difference between the masses of the different states, what will happen is that you will sort of start to see discreteness in the spectrum show up. So instead of having a nice, smooth stasis like this, what will happen is one of these states will decay and there'll be a little dip down, and then the next one will come up and it'll be a little bit up. So you'll get little oscillations in this. This is something we noticed in one of the papers I showed at the beginning, which we call oscillatory stasis. But you can derive a condition on delta m and other parameters in the theory to where you're basically going to see this and where you're not going to. So yeah, there are discretization effects that can show up, and you can get sort of a wobbly stasis as well.
But it seems unlikely that you'd ever be able to tell.
Whether or not it would, yeah. I mean,
everything involves some integral over.
Yeah, there are certainly limitations to whether we'd be able to tell if you could wobble or not. Yeah, that would probably be a little more challenging.
Another quick question?
I'm just curious about, in this type of theory, like what would the predictions be for the future of the universe? Like in lambda CDM, we have that dark energy will take over and the universe will continue to expand. Do we have something similar here, or would we get some situation like maybe you have another stasis era, or you can get that like some other type of way to pop up matter again?
Okay, very good question. I'm going to use this as a plug for a little bit of a tangent, but first of all, I should emphasize that pretty much everything I talked about today has to do with things that modifications of the cosmology before the BBN epoch began, because there are very tight constraints, going here. So if I'm trying to have the universe be in stasis, once we have constraints on how light elements are how light element abundances are evolving, try to say that 5 times fast, here, then it is much harder because we know what's the balance. We know what the balances of different nuclear abundances are. It's much harder to modify things here. So stasis, if it occurred, one would typically assume that it would have occurred over here. Now, one can dream up all sorts of weird possible scenarios that somehow maybe the universe is starting to enter into a stasis now or something, and all of these anomalies are because of that. I will leave that to more speculation, but just to say that most of what I was talking about here is stuff that won't affect the long-term future of the universe. It just affected the past. All of those states have decayed away at this point, and they don't really have any impact on the future.
So we'll leave that and other topics for future discussion, and let's thank